Welcome. The Kruskal Katona Theorem is a result about simplicial complexes. I'll just summarize a couple of these categories of geometric objects in the finite, which we can look at. Finite sets, not a good framework because there is no interesting cohomology. Also, hypergraphs in general don't have an interesting cohomology. Finite set of sets, it's essentially the same than just a finite set with more structure. But what is really starting to be interesting is if you have a finite abstract simplicial complex, a finite set of non-empty sets closed under the operation of taking finite non-empty subsets. It has one axiom, it's the simplest structure, so it's simplicity. And I like also graphs because finite simple graphs naturally give you a simplicial complex. Here we have an example of a graph. It gives you immediately a simplicial complex, not just one-dimensional, but it has also triangles. And that's how almost every topologist 100 years ago thought about graphs, as skeletons of topological spaces. And then we have also CW complexes are very popular in algebraic topology. I learned about CW complexes in the algebraic topology course I took, and but it's usually considered in the continuum, attach cells to spheres in already established structures, but you can do that very easily also in the discrete. A CW complex can be built up recursively, and of course it's a delta set because you have a natural exterior derivative, you have a natural Dirac operator, and so this delta set structure captures this perfectly. So delta set is the most general structure. There is an example of simplicial sets which kind of has more structure than a delta set, but it's less general. If you attach more structure, of course it's less general. So this is really the most general structure which you want to consider. It's a topos. You can do constructs like Cartesian products, you can do quotients, you have open set, you have a nice topology on it. And you can also, I mentioned that last time already, and it was a theme also I was pursuing a couple of years. Now you can always go from, look at these kind of like the natural numbers, so these are the natural numbers, and you go to the integers. What you learn in first grade, second grade is that they are negative integers, and you have also negative space. You can do that, and the f vector becomes negative, the Betty vector becomes negative, the curvature becomes negative. You can, essentially what you can do here, you can also extend here. But then we have a ring structure, not a semi-ring, but we have a ring structure with addition, with the coproduct as addition and the Cartesian product as multiplication. So that's the geometric framework, and this theorem of Kruskal Katona deals with the cardinalities of sets which can occur in a simplicial complex. This is captured by the f vector. So what possible f vectors can occur, and so here is a little bit of definitions. The key definition is already defined in Knuth's art of computer programming. So here's the shadow of a set of sets. So you take just from every set, you just take an element away. Or you look at all the possible cases of sets you get by taking one element away. So you have a finite set of sets. This is defined for any finite set of sets. And then you can define the shadow of one of these sets. So the shadow of 1, 2, 3, for example, is the set with 1, 2, 1, 3, and 2, 3. So you have, and then you can also look at the cardinalities. If you take a K-uniform set, meaning that we take a set of sets which have the same cardinality K, and then, of course, because you can take only K, in K different ways, you can take away one of the elements, so you have this constraint. That's true in general, and you can then ask, what about the converse? And the converse doesn't hold already for delta sets in general, not. So I have here an example of a delta set, and I wanted just to realize the F vector 3, 4, 1. No problem. I just produce a delta set where we have 3 points, 4 edges, and 1 triangle. And they are not related with each other. So this is actually an open set. So it's an open set in a simplicial complex, in a larger simplicial complex. But it's a delta set. We have a cohomology, actually the Dirac operator which we give in the structure of the delta set is just a zero matrix. So all the kernels are, the full, then we have the Fk is equal to the Bk, and these numbers in the case of positive space, right, are non-negative. And we have also this constraint Bk smaller than Fk because this is the dimension, right, which of this block, of these Hodge blocks. So yeah, in general there are no constraints, but in the case of simplicial complexes, so then there is an interesting constraint, and you can compute this using a beautiful operation on integers, which is the k-shadow operation. It's usually denoted by delta k. So we have an integer, we write this integer in an expansion, kind of cascade expansion. So you start with the largest binomial coefficient, which has n1 over k, and then n2 over k minus 1, and you do that with the greedy. You take all those things away in a similar way than you do that for the binary expansion of a number. So you can do that. I've implemented that in Mathematica. It's no problem to get this k-cascade representation. And then the shadow, the k shadow, is just when you take you replace the k by k minus 1 always, or the j by j minus 1 at the bottom. So this is a new number. And here is an example. If you take 1000 you can write as 19 over 3 plus 8 over 2 plus 3 over 1. That's the 3 cascade representation of 1000, and then you just take 1 away and you get here 180. So Donald Knuth has in his book, it's not, these are, I have only the first books physically and the rest electronically, but the first, one example which Knuth gives in his The Art of Computer Programming is kind of how many triangles can a graph with 1,000,000 edges have. If you think about this, this doesn't look easy, right? How many can you do? I mean, I have made another example here which we can just see, the same question, this Knuth question I ask, how many triangles can a graph with 5 edges have maximally? So, and then the answer is given with this Kruskal Katona Theorem, because we just make the 2 cascade expansion of 1,000,000, and that's 1414 over 2 plus 1009 over 1. And then we go backwards actually here. Then we go by the invert, that shadow operation can be inverted, and then we take 1 more. We are interested in triangles and not in edges. And then we get this, and the number is 470,700,300 triangles. Would be tough to compute this just, from going through all the possible graphs. It's sharp. I mean, you can see kind of in the case of a complete graph or complete simplicial complex, you can see it is sharp. But in terms of the F vector, one can just give relations, right? So there are constraints for the F vectors which can occur in a finite abstract simplicial complex, or in a graph. If you look at the number of complete subgraphs in a graph, so this is usually read backwards. You say Fk is smaller than delta k minus 1 of Fk minus 1, and so that's the kind of like in the example which Knuth gives in his book. So yes, so in general there are no such constraints in delta sets, but I kind of was a little bit, I was looking for level sets, this SAR, theorem gives you level sets. For example, take a manifold and you take a level set, you get another manifold. It's not a simplicity complex a priori, but you can count the number of elements and then you can see, does it satisfy this Kruskal Katona theorem? And so far I've seen it always satisfies this condition. I don't have a proof for that because in delta sets, not a priori, it doesn't need to be the case. So that's it for today.